check. Can you hear me online? Is the audio working there? Awesome, thank you. No, it was this one. Here. Okay, good afternoon. Seems like a few more people than I actually expected. Thanks for coming in on this lovely day. Thanks everybody online. So let's dig right in. What we were doing last time, and I don't remember if we introduced graphs on Thursday or before, but basically what we were doing last time, we were dealing with a new data structure called graphs. We basically represent the graph as a list of nodes, where each node has a name and the reference, or a list of nodes that it's somehow connected to. So the example that we were using was a call graph, where each node represents some person, let's say, and the list of nodes represents the people that person called directly, right? So node A, we have a node named A, and node A is calling all, or the person A is calling all, everybody in the list that is associated there with it. So starting with B, etc. It was actually better using some of these examples. So, for example, we have a graph of a call graph where we have a nodes called Amy, Billy, Claire, Dan, and Eli. We have direct relationships between Amy and Claire, right? So Amy calls Billy and Claire. Then Billy calls Dan, Claire calls nobody. Dan calls Eli, and Eli calls Claire. And one of the things that we can ask about this graph and graphs in general, but with this call graph example, was, is there a path from some person in the graph to some other person? So maybe this question means, could there be some information that Amy shared that could have made it all its way to Eli, for example, right? So we want to know not only if Amy called somebody directly, but if there is a path through somebody to Eli. So if Amy knows something, can Eli know it, right? And the way we checked it, we will look at the code in a bit. The way we checked it, of course, is first we want to know if there is a direct connection. If there is no direct connection, so if Eli isn't in the list of callees of Amy, we will check every callee of Amy if they have a path to Eli. So we have a recursive function there checking for each callee if they have a path. Let me look at the actual code. So this very simple function simply checks if we have a path between two given nodes given by their name in the given graph, right? And this holds if there are if one of two situations holds, right? So either there is a direct relationship, so node B or node A has a path to B. If B is the immediate callee of A, so that's the simple case, and we are done there, we just return true. Otherwise, if this is false, then what we need to do is to go through the list of callees, and for every callee check if that callee has a path to B. And by extension, if the callee has a path to B, then A has a path to B as well, simply through its connection to that particular callee. All was good, nice simple function, but we ran into a problem when we wanted to check graphs which contain cycles, right? So everything worked fine on our graph A, where every path basically terminates at some point, right? So we have a path to Claire from Amy, then we have a path from Amy through Billy, through Dan, through Eli, through to Claire again. But there is no way that we can end up looking at Amy again. So this was fine, and it worked fine with our function. So that's the ideal case. However, when we got to check the last graph example, and we inquired whether Amy has a path to Eli, we found out that this example actually doesn't terminate because we have a cycle in the graph. I did a little visualization here. So our problem was that we were looking whether there's a path between Amy and Eli. So we were checking whether some information from Amy that Amy could have shared could have made it all the way to Eli. And to check this, since Amy and Eli are not immediately connected, so Eli is not a direct callee of Amy, we needed to check all of the callees of Amy to see if they have a path to Eli, right? And the way that the list of callees of Amy is organized is that Billy comes first and then there's Claire. So what our function did was, okay, Amy is not the immediate, Eli is not the immediate callee of Amy, but let's see if Billy has a path to Eli, right? Billy also doesn't have Eli as the immediate callee, so we checked the callees of Billy to see whether they have a path to Eli. Now Dan also doesn't have Eli as the immediate callee, but it has two callees who might have a path to Eli, right? And the two callees are Amy and Claire. And again, because Amy comes first in the list of callees of Dan, this is the first path that we try to explore. And we end up in looking at Amy again, right? I'll get right to you. So we end up looking at Amy again, but what happens is then, to check whether Amy has a path to Eli, we again need to check all the callees, so we go to Billy again, etc., and we always explore the same path, and we end up being in a cycle. Josh?
So if you're changing the order of Dan's callees from Amy, Claire, would that
That would
resolve the issue?
resolve the issue for this particular graph, right? So we don't want a function that depends on a specific order, or you don't want to be kind of running around and fixing or accommodating the graphs, right? The order in which the callees are listed shouldn't really matter. Okay? And in general, it could be that there are cycles in both of the paths, right? So it could be not just that Dan going through Billy and Dan ends up being in a cycle, but going through Billy, Dan, or going through Claire might end up in a cycle. So our function works for some cases. Some cases can be adjusted to work with our function, right? But it doesn't work for graphs in general. Okay. Are there any questions about where this issue comes from? And okay. So that was a bummer. Then the idea that we kind of floated at the very end, and I think somebody in the room floated it or online, was to avoid going in circles, basically, by leaving breadcrumbs. I don't need to have this here. To leave breadcrumbs and keep track of where we've been, right? So in the case where we go into where we might go into a cycle, because checking for Amy's path to Eli, we have to go through Billy, Dan, ending up back at Amy, we want to know that we already dealt with Amy, right? That we know that Amy doesn't have a path through Billy, and we want to stop there. We want to know that basically this path doesn't lead anywhere. So the idea was, okay, let's keep track of where we've been, kind of leave the light on where we visited, and know that, okay, we looked at that, we might go somewhere else because we might be more productive rather than trying to run in circles. And I shared the full code of this function with you, and I'm not sure how many people actually looked at it, but don't worry, we will actually try to implement it from scratch and go through that. Okay. Why this idea of leaving a breadcrumb is important for us is not just because of graphs, right? You do need to have a way of keeping track where you've been in a graph, because you might end up being in a cycle. But this idea of keeping track of things as you go through a recursive data structure generalizes to something called an accumulator, right? An accumulator is an additional argument to your function, which keeps track of some information that you accumulate as you go through the data structure, right? And we will use this idea to actually implement a path that keeps track of its visitors. Okay. Usually, what we do with an accumulator or with an accumulator function is, the first thing is we want to keep the interface the same, right? We still want the path function that just takes a graph and two names and returns a Boolean, because we don't want to expose that we actually do keep track of the visited nodes. They are not important outside, and moreover, we don't want to put the burden of the user to tell us what to do with our accumulator. So usually the way we write functions with an accumulator is that the main body of the function just simply starts off a computation by calling a helper that kicks off the computation with the same arguments and some accumulator. So let me define that function locally. And accumulator over here. So what I will do is I will call the accumulator seen so far to represent the nodes that we visited. Now, if we try to graph name, and returns a Boolean, so it has almost the same type. We just need to decide what this data structure is that we will use to keep track. What is an appropriate data structure for this? Josh? List of names, exactly. So all we want to do is to have a collection of all the places that we visited, right? To represent where we've been. So first step, decide what kind of have multiple steps to designing a function using an accumulator. The first one is, okay, what do we actually want to accumulate? In here, it's the as already visited. Okay. So that gives us the first thing. We gave it a name. We kind of designated what it means. The next step is decide what the initial accumulator is. So at the beginning of the computation, we need to decide what is the initial state of the accumulator. In this case, because our accumulator represents the list of nodes that we already visited, at the beginning we didn't visit anything, so the accumulator is simply an empty list of nodes. Okay, so that takes care of kicking off the computation. And for the rest, so to actually implement the function, we can start with a similar structure that as we had with the originally path function. But I will, to make it a little explicit, I will write it down as a cond instead of an or with multiple cases. So the cases that we had was that actually the first thing that we did was to collect the callees of A, which was simply of A in the graph G. Now, if the given node is a callee of A, that's the simple case, we simply return true. Okay, and the alternative case was if was that we needed to check every callee of A whether each callee has a path from, whether any of the callees has a path from to the node that we're looking for. Okay, and we need an accumulator here. And this would be this. Okay. So just to reiterate, this is basically just the body of our original path searching function, kind of refactored as a conditional in here. So we either have an immediate callee of A, or otherwise we look for a callee that actually has a path to the node B. Now, in terms of accumulator, the next thing that we need to decide is how to adjust the accumulator in recursive calls. All right. So what do we do with the accumulator here? We're looking for a path from A to B. We now checked A, right? A doesn't, we are in a case where B isn't the immediate callee of A, so there is no direct immediate path, so we need to check all the callees. Josh? Can I define it outside of it? You mean this local definition?
Yeah, like what if you just define that right under capital?
I can define more than one local, but would it be the same if I define it outside? Does anybody know the answer to that? Where does this A come from? Yeah? It comes from here, right? It's the argument to the helper. If I put it outside, it would be coming from the top level A.
Right, so how is that one different?
This function is called with Amy, right? In the example that we had there, this one, right? So the initial call to path helper is Amy, who was it? I think Eli in there. Amy Eli, right? That's the initial call. A in the body of this function is Amy. The helper will not find Eli in the immediate callies of A, right? Here the callies of A are Amy. So for each callie of Amy, which is, if I remember correctly, Billy and somebody and Claire, we will have a recursive call to path helper with Billy and Claire here, right?
Does defining locally include the local allows like a dynamic like definition, so like it changes when you switch to different calls?
It changes because this is a different function every time you call it. This gets a different argument, whereas this is Amy at all times. Maybe doing this will make it a little bit more explicit, right? Yeah, this A and this A are different. Okay, that's the trick with local there. If I define it outside and I would use callies of A, it would always be the callies of Amy, not the next node that I'm looking at. Okay, so somebody online, Kishan, yes, suggested that the way we actually update the accumulator is simply deciding, okay, I checked the callies of A, B is not among the callies of A, now I'm actually going through the callies of A and calling the path helper, but at this point I know that I already checked A. So what I do is simply say, okay, just add A to the list of nodes that we've seen so far. And continue. Okay, because that's what the accumulator means. It's a list of nodes that we've already seen. At this point, we check the callies of A. At this point, we checked every callie, so when we do have this recursive call, A no longer needs to be checked. So we add it to the list of nodes that we've seen. So in this case, we had the node that was just visited. So we introduced an accumulator, decided what it means. We gave it an initial value. At the beginning, we haven't seen any nodes. We adjusted in a recursive call. We've seen the node, we added there. Are we done? Charlie?
We have one more step, which is to say new icon. Basically, if we then report if A is a member of the CMR list, then return false.
Exactly. So what we are doing here is simply, okay, we add it to the nodes that we've seen so far, but we make no use of it, right? We just add it there. We don't actually terminate it. It just means we collected the nodes that we visited. We still end up in a cycle, and we would just keep adding Amy to the same node. So what we actually need to do is to check whether the node that we are currently checking, right? So now we are considering A at this point, whether A has been in fact visited. And if it has been visited, it's the same situation as if A would have an empty list of callies, right? We already exhausted all of the callies in this OR map, so there is no more callie to check, so we simply return false in this case. Okay, so we have three cases that can happen here. Whenever we consider a node to see whether that node has a path to the final node, right? We either have already seen this node, in which case that means that we check this. There is no direct path here, so we can return false for this one. If we haven't seen it, we will check if B is in the list of immediate callees of the node that we are considering. If it is, great, we are done. If it isn't, then we check all the callees of the current node to see if any callee has a path to B, to the node that we are looking for. Okay. So basically the way this works is keeping track of where we've been, but also exhausting one direction fully and only stepping back if there is nowhere to go, if we hit a wall. Right? Either we have a node that has no callees, there are no neighbors, there's nowhere else to go, or we hit a node that we already visited and we exhausted all the possibilities for that one. Okay, so we hit a wall, we track back. So in this case, again, we start with Amy looking for Eli. We have two possibilities, right? We haven't seen Amy at the beginning. Eli is not an immediate callee of Amy, so that avoids that kind of skips those two possibilities. So what we do is we check each of the callee, each callee of Amy, whether they have a path to Eli, right? And because of the order in which we do it, the first path that we actually want to exhaust is going through Billy. Right? Billy only has one callee, so we follow it over here. Then Dan again has two possibilities, right? The connection to Amy happens to be the first one. The connection to Claire happens to be the second one. So for Dan, we want to explore the first one fully. Here we hit a wall. We've already seen Amy. Amy is in the list, right? At this point, we have seen Amy, Billy, and Dan. We're here, hit a wall, return false, which means the OR map then needs to, okay, so one of them is false, maybe another one will be true. So now we will go this way and check Claire. At this point, we've seen Amy, Billy, Dan, and Claire. Claire has an immediate connection to Eli, so we return true. So this one returns true. That means that one of the paths from Amy leads to Eli. Does that make sense? I don't see any nodding, any... I don't know if I just assume no and go through, actually step through an example, or if it's fine. Shall I step through an example? Okay, let's do that. Let me copy this thing over here and follow the conditional. So what we are trying to find out is whether there's a path between Amy and Eli. Okay, so following this function is really simple. All this function is doing at its top level is simply calling path helper. So this will transform into path helper cgraph Amy to Eli with an empty list of visited nodes, right? Okay. Now the first case, or the first call with to path helper, we have an empty list of visited nodes. That means A is definitely not a member of scene so far, so we skip the first condition. We checked whether B is in the list of callees of A, right? In this case, let me do it like this. callees of Amy are Billy and Claire, right? B is not a member, B being Eli is not a member of Billy or Claire. That means that we need to explore the paths leading from there. So at this point, our function branches into two calls, right? The OR map will call path helper for each of the callees of Amy. So what we have here is a call to path helper with Billy and with Amy added to the list of visited nodes. And we have another call, I'll write it down here, with Claire, with Amy added, right? Now, this call to path helper will check whether, first thing it will check is whether Billy is in the list of nodes that we've seen so far. There's only Amy, so Billy is not there. So first condition doesn't apply. Second condition is Eli in the list of callees of Billy, where the list of callees of Billy is simply Dan, right? Eli is not Dan, so the second condition doesn't apply. So we have a recursive call to path helper for each of the callees of Billy, which is only Dan. So what happens here is we have a call with Dan. We already visited Billy, so we add it to the list of nodes that we've seen, right? First condition is Dan a member of Seen So Far, where Seen So Far is Billy and Amy? It's not, so the first condition doesn't apply. Second condition is Eli in the list of callees of Dan, where the list of callees of Dan is Amy and Claire. Eli is not there, so the second condition doesn't apply. So what we have again is let me do this like this. We have another call to path helper, actually two in total, because of the OR map that maps over Amy and Claire. We check Amy with the list that now contains Dan because we just visited Dan. And if that one doesn't work out, then OR map will do another attempt and process Claire. Right? Now, this call to path helper is really simple because the first condition applies, right? We've seen Amy. Amy is in the list of Seen So Far. So in this case, we simply return false. So this one will simply go to false. Right? We are done with that branch. But because of the OR map that's being called from here, we still want to explore the path that goes through Claire. So that's Dan's other path. Going there, we check whether we've already seen Claire. We didn't. Okay. So then we look at the callees of Claire, and Claire's callees are Eli as the only one, which means that the second condition applies, right? So we return true, which means that one of the cases that ORMAP checked was true. In this case, right, where we were exploring Amy and Claire, Amy failed because we've already seen Amy, so there is no path through there. But Claire succeeded, so we get a true there. So the ORMAP returns true. In here we return true. In here, and finally the whole thing returns true. And we have a call that the ORMAP didn't have to check. Okay, does that help a little bit? Just a smidge. Okay. So the idea is at each point we have three ways of how the current call to path helper terminates. Either we have seen that node simply return false, or the second argument is actually in the list of callees return true, or the list of callees is actually empty, in which case the ORMAP will return false. Okay, and that's how we terminate. So just to reiterate that, where is it? Our original function only had two ways of terminating, right? We either found found B in the list of callees, in which case we return true, our function terminated, or we had an empty list of callees, in which case we returned false and terminated. What was missing there was terminating on the condition that we've already seen the node, right? Because if you look at this recursive call, we are following a path, but there is nothing that kind of reduces the number of calls that we still need to make. This is where the accumulator comes in. Right? It introduces another terminating condition, and that is the one when we actually hit a cycle. We still follow the potentially cyclic structure of the graph. But because this list always grows, we are never taking anything out of it. Right? We are always adding more nodes that we already checked. Eventually all calls to path helper have to terminate. Because we need to reach a case where one of these calls to path helper, if nothing of these conditions holds, one of these calls to path helper will have a full list of nodes in the nodes seen so far. Right? And that's where we terminate. There's a more formal way to actually prove this, but the intuition is that eventually there needs to be a call that will contain all the nodes that we've seen so far. We either terminate early or we explore the whole graph, and that's when we end. Okay, so this is actually what I wanted to add here. Is actually the fourth step is exploit the accumulator to compute the result, which helps us by actually establishing that we've already explored some path in the graph. What we did here, what this function implements, is what is called a depth-first search. Right? Because what we do is, at each point, we kind of keep track that, okay, there's Claire to explore here, but we try our best to go all the way until we hit a wall, and only then we go back as little as possible to check another path fully, right? So that's why we actually, to find the path to Eli, we have to go through Billy, then Claire to Eli, although there's a shorter path through Claire directly to Eli. So if the order was flipped, we would almost immediately find that there's a path. Any questions? Okay. You will do a lot more with graphs when you do algorithms, including depth first search and breadth first search, which actually kind of goes as little as possible in all directions. And only if you didn't find something in that initial exploration, you go one level deeper wherever you can, etc. But this is kind of an initial overview, and why we actually, in some cases, we actually need to add an accumulator to do that. The next example that I actually want to look at for an accumulator is not a function that needs an accumulator, but a function that benefits from an accumulator to make it more efficient. Okay. So unless there are more questions about this, let me actually check how many typos I made and whether this runs. Surprisingly, none. Okay. So as another example for using an accumulator, let's leave graphs be graphs and just work with lists for a little bit. So here's an example. Let's say that I have a list of numbers, right? And the list of numbers represents the list of relative distances between some points. Let's say I'm traveling through multiple towns, and I go from town A to town B, and the distance from town A to town B is 5. Then I go one further, the distance is 1 to C. Then I go to D, that's another 6 miles, let's say. Then I go to town E, and that's another 9 miles. So I have the relative distances that I traveled along. And we want to turn it into a list of absolute distances, right? So something that expresses, okay, starting with town A, it took me 5 miles to get to town B, 6 miles to get to town C in total, 12 miles in total to get to town D, and 21 miles to get from A to E all the way. Okay, so we want to write a function like this. This is expressed as a check expect. And let's try to write this function using just the basic list template without thinking about accumulators, and actually trying to express it using a normal recursion. The empty case, let me copy this. So if I have an empty list of relative distances, what is the corresponding list of absolute distances? Charlie? It's also empty. Right, nothing to compute there. Boring case. Okay. So this is the easy part. It's empty. Now to find out what we do in the recursive case, let's add one by one a few examples. So let's say that I have a list of 9, right? From the starting from the right. What is the absolute distance between 2 points if I only have 9 as the relative distance? I have a list with one relative distance, meaning I'm traveling between 2 points. What is the absolute distance between those 2 points? Charlie?
Yeah,
It's also 9. Okay. What if I add one more? To travel from A to B takes me 6 miles. To travel from B to C takes me 9 miles, right? So what is the distance from A to C in total? Yeah? 15. But what is the list? Yeah? 6 and then 15, exactly. Still only takes me 6 miles to get from A to B, but then from A to C, it's 15 miles in total. Okay. Adding another one to the front. What happens with the result? Yeah? Uh-huh. Uh-huh. And 16, exactly. Every time I add something to the front of the list, I add it to the front of the list in the output, right? And I bump each of the remaining elements by the same amount. And finally, building up to a list that contains 5 in the first position, I put 5 into the front of this list and add 5 to each of those remaining things. So this gives me a hint on what I should do for my const case, my recursive call. Right? There is a mistake in my template. So I need to call this on the rest. So what I do here, as we said, every time I'm considering a new element, I put it in the front of the list, right? So going from this list, added 1 to the front. And then I needed a way of adding that first element to all the remaining elements. How could we do this easily? How about we use a map? What I'm trying to do is to take each element and add the first element to it, right? And the input to map is actually whatever I get from processing the rest of the list. Again, add the first element and then update all the remaining elements of the list by adding the first element to it, right? Every time we have a new one in the front, we need to update the absolute distances because it adds that much to our travel distance. Does it make sense? I see some nodding, some doubtful faces. Is there something that doesn't make sense about this implementation? Okay, if we run this, let's check if I've got this typos. Okay. Well, this is good. We have a function that works. What is kind of annoying about this function? Is there something that irks any computer scientist in this room or online? Yeah? Exactly. So not only we are going through the list and adding counting the first element to the front of the list every time we have a new element, right? We are mapping over the remainder of the list every time we go through there. So in the end, we are not only going once through the list, but at each point we are going n minus 1 times through the list, right? Because we have a map that goes through each element of the remainder of the list and adds to that. So what we end up here is for a list of n elements, right, is we go through it n times, then n minus 1, then n minus 2, until we reach 1, which means we are roughly processing the list and times n minus 1 divided by 2. Right? Which to people who analyze algorithms is as bad as just doing n squared steps, right? Because that's the kind of upper bounds. They say, well, I'm ignoring this. I'm ignoring that you are doing minus 1 here, and it's all the same to me. Okay. So what we say is that this approach to actually updating the distances is quadratic in the number of elements of the list. Okay, which is not the end of the world, but it's not great either. Now, how could we introduce an accumulator and exploit an accumulator and save ourselves going through the list again and again every time we have a new relative distance? Yeah?
That's like the sum of all the previous numbers.
Exactly. What we need to do is kind of switch our mindset, and instead of going from the back of the list, right, because that's what forces us every time we add a new element to revisit all the remaining that we already computed, is like, let's just go from the front and remember how much we traveled so far. So apps, let's do an updated version. And again, we will use the same approach where we have a local definition, and we simply call a helper that we define that takes the same list and remembers the distance traveled so far. So let me apps helper. List of numbers, distance so far. Okay, so that's our step number 1. Decide represents. Let me write down the signature as well. We have a list of numbers and a number, and we return a list of numbers. Okay. Then our second step was deciding what the initial state of the accumulator is. Josh? Did you? Okay. So, since our accumulator represents the distance traveled so far, before we even started with the list, the distance is 0, right? So the initial state of the accumulator has to be 0. Okay. And now, the process in the accumulator itself also needs to follow the list template, right? Because we need to go through the elements. So either we use a list abstraction or we use the list template. So let me do this. And cons when, where we have a first LON and we have a rest LON, which means we have a recursive call using somehow using the accumulator. Okay, let me reorganize this. Okay, does anything change about the base case? If we have an empty list, do we need to do anything else? We still return an empty list of absolute distances, so that doesn't change. That takes care of one, simply enough. So let's do the third step here, which is okay. So we have a recursive call with the rest of the list of numbers. We do something about the first one. We'll get to that in a bit. But what we want to do is now decide how do we actually update the accumulator. So what do we do with the accumulator when we call recursively? Take out the first relative distance, do something with it, whatever. But then when we go to the next one, we have the distance traveled so far, right? And we have the distance to the next town. Josh? Exactly, because we have the distance that we traveled so far, and we have the relative distance to the next town. So when we go to the next one, the distance so far is exactly the relative distance to the next one with the absolute distance that we covered so far, right? And that's the recursive call there with an updated accumulator. Okay, last bit is how do we actually use the accumulator? How do we convert this relative distance to an absolute distance? When we start with the list over there, right? Our accumulator starts with 0. Right? So we have a relative distance of 5. The absolute distance is 5 again. We didn't travel any distance so far. We only have one relative distance, so we traveled so far. So we traveled 5 miles, right? When we get to the next one, we already traveled 5 miles, and the next town is 1 mile away, right? So the absolute distance to the next town will be the distance that we traveled plus the distance to the next town. So what we do here is add the distance so far to the relative distance. So we actually use the same computation that we did for that. Here we are accumulating the distance so far. Here we are actually just saying what the accumulated distance is, right? with the distance to the next town. And this gives us the function. Let me check. It actually runs. Okay. So we use an accumulator to remember how much we traveled so far. And that means for each element, where each element is a relative distance, the absolute distance for that element will be the distance so far plus the relative distance to the next point, right? And the advantage of using an accumulator here is that we just go through the list once. Right? We don't need to go back and update all the previous ones that we already computed using a map. We are remembering how much we traveled and using that fact to simply process each element only once. So we get what we call a linear performance because we go exactly once through the list. Any questions? We'll do a few more examples on Wednesday, but right now, because we are at the end of our time, I just want to recap basically what the steps are of working with an accumulator, right? When we identify that we have a problem that might benefit from using one. So the first one was decide what the accumulator or represents, and the examples were of nodes visited or distance so far. Then the next step is decide what the initial state of the is. And again, in our examples, we had empty list of nodes and zero distance so far. Then the third part was how to update on recursive calls. Where we had add the node just seen to the nodes visited, or add the current to distance to the absolute distance so far. And finally, exploit to compute the result. Here we simply return false if the node has been visited, and add the far. Okay, so those are basically the 4 steps that you will need to go through when you are introducing an accumulator, and we will see a few more examples of that on Wednesday. On your free time, if you have, idle 5 minutes, what I would like you to think about is 2 ways of defining a function that reverses a list, right? One without accumulator, just using the list template, going through the list, deciding what do you return. For an empty one, what do you return if you add one element to the empty one, etc. And then how we might exploit an accumulator, how we might use an accumulator to reverse a list more efficiently. Okay, we're out of time. I don't want to keep you. Let me know if there are any questions while we all pack up and leave. And otherwise, have a good rest of today, and I'll see you on Wednesday. Thanks so much for coming and listening. Jake, regarding the exam, we are working on it. Hopefully we can release the grades. There are some logistical issues that we have.